Hello, welcome to lecture number 3. So we are going to today talk about another application of lasers, which is holography. Uh, Holography was invented in 1948, 47-48 by Dennis Gaber. And actually, it was the invention of laser that basically set this whole area free. So let me qualify that. So holography, we will see, essentially is trying to capture something which is beyond just what is captured in a typical image in a camera. So if one looks at, one is very used to photographs in 2D, which is basically a sort of the message is simply in the intensity variation across the photograph, right? There is no notion of sort of a depth perception in the photograph. There is no notion of a parallax where I look at the same object from different views, and these various other perspectives are not at all apparent in a normal photograph, simply because the normal photograph contains only a intensity distribution or an intensity map in 2D. So what you have in holography is actually beyond that. The Greek word holo, which means whole, and gram, which would mean message. So, holography refers to essentially an ability to capture this whole message, which would mean that the light that appears out of the hologram, okay, so when the hologram is looked at, the light that appears out of the hologram is similar or almost similar or as close as possible to the real object scattering that light. So one has to not only capture the phase of the field, but also capture the amplitude information. Of course, in a typical photograph, the amplitude or intensity, which is amplitude squared, is easily captured. But what one wants to capture is basically this phase as well as amplitude together. Now, you know how conventional photography works. In conventional photography, particularly in olden times when we used to use normal cameras, what you had was in a camera film. This is of course also true for a pixelated device. Okay, I mean the principle is true. In a camera film, what you have is basically a photochemical reaction. What you have is basically silver halide crystals which are distributed in a medium across a thin layer, and in presence of light, right, photochemical reaction happens, and when you process the film, what you do is basically you release these silver ions. So silver in its metallic form, okay, silver in its metallic form is released, and that's how you form this distinction. And the amount of silver that is released depends on the intensity. So larger the intensity of light, greater the silver released, more opaque the film or the so-called negative becomes. That is, if you pass light through such a film, then you would get dark where there is more exposure to light, and basically lighter where there is less exposure to light. And so this is a reversed kind of this thing. That's why it's called a negative. So that is how the conventional photography or the conventional recording of information worked in normal cameras. Now, of course, there are variety of films. So these films are characterized by a variety of things. But then you can really have, think of it as very, very small crystals, and the typical pixel that one can associate, that is what one is calling pixel as the smallest information size, smallest spatial size where you contain the information, where information is contained, and that is of the order in a typical film is can be as small as about 0.125 micrometers. Right, that's the kind of size one is talking about. Not just that, if you look at the intensity variation, okay, so there is a dynamic range intensity variation which typically these films can capture is essentially 5 orders of magnitude, right? 5 orders of magnitude, which is actually pretty large. So that is the kind of that is the kind of range that one is talking about. Now, if you look at our typical CCD cameras, just as information, if you look at our typical CCD cameras, the typical pixel size would be about 10 micrometers in contrast to 0.125 microns there. And the intensity variation will be only about 2 to 3 orders, maybe 3 orders of magnitude sensitivity to variation in the intensity. So that's the kind of numbers that one is looking at. So really, the films actually do better, but of course, it involves a lot of processing. All right. So let's come back to hologram. So in a hologram, what you want is, remember that you want to capture both the phase and magnitude or amplitude, right? In order to do that, what one needs is actually have some sort of, because you see, phase is going to be definite only if there is a notion of a reference, right? Phase is always with respect to something. So there is going to be a reference, and we want this reference to be steady, okay? And that notion is captured by the characteristics of lasers, which they are coherent. When you record the hologram, should contain both these aspects, right? It should contain the phase aspect as well as the amplitude aspect. So imagine the following situation. Imagine I have a point source, right? So the point source, which is basically emitting spherical wavefronts that propagate, right? And this wavefront, this spherical wavefront now falls on a recording screen. And at the same time, what you have is a reference beam. Okay, so I'm actually using a different color, but they are of the same frequency. So this is just for, so when I'm looking at different colors, so what I'm saying is I got now a reference beam, which is a plane wave, which is also simultaneously falling on the screen. So if I'm looking at the wavefronts, I'm looking at planar wavefronts, right? Now you see both of these wavefronts are falling on the screen. So what you will see is essentially, so just imagine, so let me look at it in a more detailed manner here. So let me look at this wavefront, which is just on top of the screen. And I have another wavefront, which is arising from the plane wave, which is the planar wavefront, right? You clearly see that these two wavefronts, let's say, are in phase here. So what you are recorded now is actually an interference pattern on top of this film. So, okay, so let me put down some numbers. Let's say the distance between the point source and the film is S. And let's say that the intensity I1, let's call this one I2, right? And then I want to write down what is the total intensity that I record. So we can quickly write down my I total is pi over 2 S lambda, where lambda is the wavelength one is talking about, times rho square where rho is now the radial distance onto the screen, right? So this is the radial distance rho on the screen from the center, right? So this becomes my I total. What we have is basically this cosine square sum alpha times rho square. That's the kind of functional dependence that you have on the screen. So that you have these circular fringes, and as your rho increases, they of course get closer and closer, and that's the manner in which. Now, of course, you can clearly set that. Imagine at rho equal to 0, I do get basically the maximum, and as I change now my rho, right? As I keep changing rho, maxima and minima, I get these fringes. So what one is recording is actually uh, not the not either the light from the source or from a reference, but recording an interference pattern between the two, right? So what is the purpose? So now let's say I have the same frame, okay? I have the same frame, and now on this, I come in with my original reference, which was just a plane wave. So you see that this plane wave is going to be diffracted, right? Diffracted so in direction, appearing as though there was a source which was kept at the same distance as we had recorded it. So right, this appears to be, so what if you are looking from, if you are looking at if you are looking at this film from here, you're going to see that you're going to observe a virtual source S, which is essentially emitting this light. So now you see I have captured the source. I have captured the actual light that is emitted from the source as though the real source was there. But after all, what you have is a recording on the film. This particular object is basically what is famous as the Gabor zone plate. We will not get into the business of zone plates, but then it is in itself a topic. There's a Fresnel zone plate which is used widely as a flat lens and so on. So I'll come back to. I'll probably not have time for that, but you have other things which I have not talked about. The other thing is that actually the diffraction is not only outward, there is also a inward diffraction. There is also a diffraction which is in that direction, so the every light is actually so as to form another source, but now this is a real focusing of the light, and this is a real image. So what we have here, what we are watching earlier, was a virtual image. That is what captured the original source, and now what we have is a real image. If I had taken a photograph of this, image of the source, I would have basically got a point source there and basically light everywhere with large intensity at the center and lower intensity everywhere. Then I would say that yes, indeed, the source is captured in that region of the plate. But in this case, you cannot pin down and say there is a one-to-one correspondence between the point and the source. So the source is effectively captured as a whole in this whole pattern across the hologram. So that is important. So there is no, I think this is important, there is no one-to-one correspondence between the source, between the object and the image that is captured. The second important issue is that the phase information is contained in the interference pattern. And you also have the amplitude information. Where is the amplitude information? The amplitude information is contained in the contrast of the fringes. So right, so in the fringe contrast. So greater is the amount of intensity, greater is going to be the better is going to higher is going to be the fringe contrast. Multiple possibilities, because now what you have is actually you are capturing the it is as though the original source has been replaced by merely a plate, okay, which contains the whole information that ever could be captured from an object. And you can say any arbitrary object would simply be a collection of these point sources at that point. So that is of course clear. Now all right, so let me, of course, before I go to the off-axis hologram, let me just make a few more comments. The comment which I want to make is that whenever I have such a hologram like the one which I said earlier, Geber's own plate, so you see that whenever you have this cosine square alpha r square dependence, okay, then you basically produce the 0th order and the plus minus first. So what is the 0th order? 0th order is basically the light going through without getting scattered. The first order, positive one order, is the virtual image. The negative order is basically the real image. So for a sinusoidal variation, or one basically gets only these three orders. That is one thing to note. Then you will see that when I ensure that the electric field associated with the source and the electric associated with the reference field both are of the comparable orders, then you see that one indeed gets absolute zero, right? So you can check that out. So let us look at this equation, and you can clearly see that so for example, when I1 equals to I2, what will be 2I, and you have minus 2I, so that takes care of that. And then as you get maxima and minima, so when you get zeros of the cosine, you would see we get absolute cancellation. So you see that if I arrange my intensities to be comparable, I would start getting, I would start basically having these absolute maximas and minimas. Now there is a issue with recording. So let me, of course, make another comment. The issue with recording is the following, right? Emulsions that one uses, they are incapable of responding linearly. So linear response is what one wants. That is, if I have twice the amount of intensity, similarly twice the amount of, for example, silver ions have to be released. So that kind of a linear response is what one expects, but the emulsions do not really respond linearly at all the levels of irradiances. So what happens is there are going to be distortions when you develop. So when there are distortions, these distortions typically take you away from this nice sine square or cosine square kind of so there are multiple orders that you start getting because of distortions. So there is of course a small solution that people do. What one does is, so you have the original intensities. So what you do is you increase the reference intensities, and then you have, of course, the variation of the so you have the modulation which is there. And let me again use this alpha rho square. So you see that if you come up with something like this, where you see you have increased the background, you have some finite background here, okay, this is coming largely out of the reference, and because of this finite background, you will see that you start making better holograms. where so because these emulsions do not respond linearly at low light levels, they do at beyond a certain exposure. So you start getting better response to the variation in the intensity. Right. So these are some issues that are there with these recording such holograms. So local there is a local variation. There is a local variation in the fringe contrast, and that is what I associated with amplitude information. And then there is a fringe spacing, right? And that is what I'm associating with phase information. Right? Clearly, you can see that both these aspects are extremely important for us to record a hologram. All right. So the dream film would be one where we have extremely high resolution in the film and extremely large dynamic range of response to intensity variation, so that one can basically get the best hologram that one can record. All right. So now let us come to this business of off-axis holograms. Off-axis hologram. So let me quickly first draw uh, the setup, and then I'll get back to you. All right. So this is the setup for my off-axis hologram. So the object is the following. This I have got is a laser source. It is emitting radiation. What I do is I put in a aperture and a lens setup to collimate the beam. Okay, so I will collimate this beam and make it large enough. And then what I do is put this beam through a beam splitter. Okay, wherein partially the beam, in the best of scenario, one has to arrange them so that the eventual intensity on the film is equal. So anyway, partial beam is taken away. This beam goes up, meets mirror 1, then comes down towards mirror 2, from where it gets reflects and falls uniformly at an angle on the recording film. Right? Right? And at the same time, now let's follow the path of the other beam. The other beam goes straight through the beam splitter. It goes and falls on the object which I want to record, and that light which is from the object gets scattered onto the film. So this is the scattered wavefront, and this wavefront is not necessarily planar. Unlike the reference wavefront, this wavefront would actually contain the information associated with the object. Right? So that is the kind of wavefront that is falling on the. So on the screen, one is recording essentially the reference light and the scattered light. So let me just now look at the orientation of the film with respect to the reference. So this is my film again, right? And this is my E reference. And you see that the reference is falling onto the film at an angle, let's call it alpha from the normal. And there is a path difference delta, which is a uniform variation across the film along the x direction. So that's a kind of setup that one has. We will again look at it mathematically, but okay. First, just understand the physical process. And now what one wants to do, once one has recorded the hologram, this is the recording process. Okay. So you see in hologram, there's always two-step process. One is to the recording process, and now what wants to do is one wants to do reconstruction. That is, once you are recorded, you want to get back the same information. What you now do is take the same, I'll try to draw it here. So this is the setup for reconstruction. Yeah, so reconstruction looks like this. What we have is the film, and then we have a reference. Remember, reference is along the similar direction as the original reference had been. Now what you see is that the reference gets scattered off in this direction, creating a virtual image of that original object, right? Not just this virtual image, if you move around along this line, you will actually get different perspectives of the same object. And you also get a very inverted, inside out image, which is located here. This is the real image, which also is focused on. So you see, in an off-axis hologram, you got the reference that, of course, part of it goes through. So there's parallel lines around the reference. And then what you get is a scattered light. This is the first order, which is arising largely from, as though the light is coming from the original object. So let us now look at it mathematically a little bit, and so that we can get to terms with exactly each of those objects and how they arise. So what I'm doing is, first let me just describe for you first just the reference light. So okay, so my E reference is what I'm calling it as. It has got some amplitude R, and it has got the same frequency I omega t plus some spatially dependent phase factor. This is the phi, is the phase at the film, right? It is tilted. So remember that this phi is actually 2 pi over lambda times delta where remember what was delta? Delta is simply x times sine alpha. Alpha was, remember, the angle at which we came in. Let me just remind you of alpha. So alpha was precisely this angle. So the delta, which is the path difference along the direction, so along the spatial location x along the film, depends on this angle alpha, and hence this is what is my path difference delta, which gives me this uniformly linearly varying phase across the film. That's my reference beam. Now if I'm looking at my object, beam, right, or the signal, if you like, my E signal is simply S. Remember that the amplitude now is not uniform like in the other case. The amplitude itself is a function of x and y, the film coordinates. And they have, of course, the frequency of the laser was the same because we have split the same beam into two parts. And the phase theta is again a function of x and y, right, which is different at different points on the film. So this is precisely what is my E reference and E signal. So if I'm looking at intensity of the signal, so let's say I take a camera and I look at what is the intensity I would record, that will be proportional to this E signal square, which will simply be mod S xy mod square, right? It will simply be the usual amplitude record. But what we want to do in the hologram is also to record this theta carefully, and as well as S. So we do the following. So for recording, what I do is I look at the total field at the film, which is the E reference coming from the reference and E signal coming from the object. And then what I do is record the intensity, total intensity of this object, because that's what my film records, which is, as you know, is simply ER. Now let me just keep the first letters, ER plus ES times ER plus ES complex conjugate, right? So this is what my intensity is. So let's work out all the corresponding terms. So my I total, this is the recording part, X. So eventually what I get is the following. I get R square plus S square plus R times S exponential I. So see, plus minus theta, omega t's get cancelled. And what I get is basically something stationary, which is theta minus phi plus R times S times exponential minus I theta minus phi. Right? So this is essentially what you record on the film. So you can, the transmittance of the recorded film, right? Transmittance of the recorded film is basically proportional to this recorded total intensity, right? So what do I do? Now I need to do reconstruction. So in reconstruction, what I have the the holographic field that I generate is going to be proportional to the transmittance, which is there, and this film, the input to this transmittance is the E reference, which is exactly same as what we had put in earlier. So let us just write out all the elements. So what you get is basically E. H is R square plus S square times ER, right? Plus R square times S exponential I omega t plus theta plus R square times S exponential I 2 phi times exponential I omega t minus theta. Now let's interpret each of these films, each of these terms.